All right, here we're going to start talking about things carbocations can do. And I'm going to do this in relationship to alcohols, because that's what this chapter we're talking about is. So one of the first things that you know that a carbocation can do is that it can react with a nucleophile. So let's give you an example of a carbocation reacting with a nucleophile. So let's take T-butanol and react it with hydrochloric acid. Let's make it hydrobromic acid this time, make it a little bit more interesting. The first step in the reaction is alcohols react with acids to deprotonate them. In this way, the alcohol is reacting as a base. The acid is an acid. Bases are proton acceptors. Bases are proton acceptors. Acids are proton donors. So the base takes the proton from the acid. So that turns that hydroxide into water, which is now a phenomenally good leaving group. Because it's tertiary, it can't really react, and we don't have heat added. This is going to react via an SN1 type mechanism where the leaving group is just going to leave. After the leaving group leaves, you form the tertiary carbocation. So again, we're going to focus on this carbocation. I'm going to use this tertiary carbocation in the following slides to show you the reactions of carbocations. But for right now, we're going to see how it reacts with a nucleophile. So this carbocation is going to look around and it's going to say, okay, where's the strongest nucleophile? What do I have in the strongest quantity that's going to react? It's going to see the bromide. The bromide nucleophile is going to come in and react with the carbocation to form an alkyl halide. So that's one thing a carbocation can do, react with a nucleophile. This is an example of an SN1 reaction. All right. Something else a carbocation can do is eliminate a beta hydrogen. So again, we're going to start with the carbocation. You can go back and look and see how that's formed. We're going to react this carbocation. We need a little bit of heat. And let's remember what was formed when this carbocation formed. Water. So now this is an E1 mechanism. Heat and a base will react together to undergo beta hydrogen elimination. So this is the alpha carbon right here. That's the one that was bonded into the leaving group, the one that formed our carbocation. All three of these carbons are then therefore the beta carbons. Any of them, they're all equivalent, they're all the same. So we're just going to eliminate one of these beta hydrogens. So during the elimination of the beta hydrogen, the base pulls the proton off. The electrons that were in the carbon-hydrogen bond swing down to make a double bond. So the product of this reaction is this alkene. Let me name it for you. This is 2-methyl propene. Alkene tells you that that's like the main functional group that's present in this molecule, so it changes the ending to propene. The double bond has to be across the lowest numbers, so it's across carbons 1 and 2, and the methyl group is over here at number 2. So this is 2-methyl propene. So carbocations can react with a nucleophile, SN1. They can eliminate a beta hydrogen, E1. Other things carbocations can do. They can resonate. So this was actually a question that was of somewhat importance on your first exam, or your second exam rather, sorry. Let's do a full mechanism here. We're going to react this. Oh my goodness. Oh, excuse me. We're going to react this allylic alcohol. It's allylic because the alcohol is 1 carbon off of a double bond. We'll react it with hydrochloric acid. When an alcohol sees an acid, it gets protonated. The products of the protonation turns the hydroxide into a really good leaving group, water. In this case, because it is allylic, the leaving group will simply leave to form the particularly stabilized allylic carbocation. So right here, I'm going to just number these as we go. We have the carbocation in carbon number 3 and the double bonds across carbons 1 and 2. This is not a primary carbocation. I know it's your first instinct to say this is primary. It is not a primary carbocation. It is allylic. Allylic and benzylic carbocations are stabilized by resonance. So one thing that this carbocation can do is resonate. The products of the resonance look like this. Now the carbocation is at carbon number 1 and the double bond is across 2 and 3. It becomes more important when you don't have a symmetric double bond like this, but carbocations can resonate. Then this carbocation can do other things. The carbocation could eliminate a beta hydrogen from here. This resonating carbocation could react with a nucleophile, but it can resonate. The last and hardest thing that a carbocation can do is rearrange. This is not easy. It's one of the things that students struggle with the most. The easiest way I can put it is, if a carbocation can rearrange to form a more stable carbocation, it will rearrange to form a more stable carbocation. So let me give you an example and show you what a rearrangement would look like. Let's take a look at this alcohol. And again, we're going to react it with an acid. And for this particular one, we are going to heat it. Okay, so let's work through the mechanism. When an alcohol sees an acid, it gets protonated. That turns the hydroxide into good leaving group water. It's on a secondary carbon atom, so the leaving group will leave. Now let's analyze this carbocation. This carbocation is secondary. It's a stable carbocation, but it could become more stable. Look one carbon next door. If we could get this carbocation to switch places with this methyl group, this carbocation can go from being secondary to being tertiary. If a secondary carbocation can rearrange to become tertiary, it will. It can shift a methyl group, a hydrogen, a benzene ring. It can shift a number of different things in order to become tertiary. So this is called a 1,2 methyl migration or methyl shift. Where the numbers come from, this is carbon number 1, this is carbon number 2. The methyl group is going to go from carbon number 2 to carbon number 1. So the mechanism for that looks like this. This whole methyl group moves. After the rearrangement, you have changed the carbon skeleton of your alcohol. So over here, you know, at carbon number 1, 2, 3, we had 2 methyl groups. Now at carbon number 1, 2, 3, we only have 1. So you can see our carbon skeleton has fundamentally changed because the carbocation wanted to rearrange. So now let's take a look and see what's going to happen here. Now that we've rearranged our carbocation, we have heat involved. Heat is going to promote the elimination reaction. So we look around and we see, okay, well, we've got beta hydrogens here, but if I eliminated one of those beta hydrogens, I would form a di-substituted alkene. This is the alpha position, so here's the beta position. I have a beta hydrogen right here, If I eliminate that beta hydrogen, I'm going to form a tetrasubstituted alkene. That's the reaction that's going to occur. So we'll take, chloride will do it. Water is more likely as a reactant, as a base. The water is going to deprotonate the beta hydrogen. The electrons swing over to make the double bond. So the product of this rearrangement looks like this. So if a carbocation can rearrange to form a more stable carbocation, it will rearrange to form a more stable carbocation. Let me show you one more example of this. It's just going to take me a second to, here we go, put in a new slide. Let's do another example of a carbocation rearrangement. So here we have 1, 2. Sorry, my notes are a little weird. Here we go. We're going to react this with water and heat. Okay, so we're going to analyze and see what happens. It's going to be an elimination reaction because heat is added. Water is a protic solvent. Protic then is going to promote E1 mechanisms. This is a secondary alkyl halide. The secondary alkyl halide under E1 conditions can eliminate, can have the leaving group simply leave. We form a tertiary carbocation. Now, here's where you take a look around and say, can my carbocation rearrange? If we look over here, if the carbocation and it took a hydrogen or it took a methyl group over here, we would either stay secondary or we become primary. So we're not going to rearrange over here to the right. Over here to the left, if this hydrogen switched places with the carbocation, then the carbocation can become tertiary. This is called a 1,2 hydride shift. So in this way, what happens? This hydrogen moves next door. That switches places with it. It's a terrible way of thinking about it, because that's not really what happens chemically, but it's the way you can think about it. The hydrogen now is over here. The carbocation now is over here. The secondary carbocation became tertiary. So now that we have our tertiary carbocation, we look around and see what it can do. React with a nucleophile, eliminate a beta hydrogen, resonate. This guy can't resonate. It's not going to rearrange any further because it's already tertiary. We have heat involved, so the reaction is going to occur E1. So we're going to look and find the beta hydrogen to eliminate it. We've got beta hydrogens at this carbon, or at this carbon. If we eliminate the beta hydrogen over here, we're going to form the more substituted double bond. So this hydrogen gets removed. The electrons swing down. The product of this is that molecule there. I'm going to name it for you. This is 2-methyl. 2-pentene. All right, let's do just one more example of a carbocation rearrangement. All right, let's do it on a ring. I know how much you guys love rings. We have an alcohol here. This was supposed to be a 6-membered ring. There we go. We got 2 methyl groups over there. We're going to react this molecule, or this molecule, we'll react it with hydrochloric acid, and we're going to heat it again. First step, alcohol sees acid, alcohol gets protonated. I want that to start to become totally second nature. Alcohol sees acid, alcohol gets protonated. Now we're under SN1 type conditions, or 1 type conditions, because we have an alcohol and we're in protic solvents. We're going to have the leaving group simply leave. Now it's time to analyze the carbocation. This is a secondary carbocation. Look to its neighbors, just one next door. If we switched places with hydrogens next door, it would still be secondary. That's not going to happen. If we look next door, if we could switch places with one of these methyl groups, we would become tertiary. So this is going to be a 1,2 hydrogen migration, or a 1,2 methyl migration, 1,2 methyl shift. The products of the reaction after this shift, let me draw that better. There we go. One of the methyl groups moves and it switches places. You form a tertiary carbocation. So again, if a carbocation can rearrange, it will rearrange. Now we see that we've heated this. I like to use water as my base. We're going to see where we're going to form the double bond. Alpha is right where the carbocation is. We have beta hydrogens here. If we formed a double bond, that would be tri-substituted. Beta hydrogens are over here. That would be di-substituted. Beta hydrogen over here would form tetrasubstituted. That's going to be the beta hydrogen that gets eliminated in this E1 mechanism. If a carbocation can rearrange, it will rearrange. So how do you get around that? What do you do if you want to have a secondary alcohol, but you don't want any possibility of rearrangement? You use the special reagent POCl3. So this is what POCl3 looks like. POCl, Cl, Cl. And you do it in the presence of pyridine. This is pyridine. Pyridine is a non-nucleophilic base. It just kind of mops up any acid that forms. It's used for E2 elimination on secondary alcohols with no possibility of carbocations. It basically forces it to go E2. No carbocation can be formed, therefore no rearrangement. So let me show you a mechanism of this. You don't really need to know the mechanism that much, but I'll show you what happens. The alcohol reacts at the phosphorus and pushes one of the chlorides away. This is what the product looks like. What this basically does is it changes the alcohol into a really good leaving group now. Pyridine, like I said, is a non-nucleophilic base. This non-nucleophilic base comes through to deprotonate that alcohol. Now, rather than turning it into water, which is a good leaving group, and it just leaves to form the carbocation, now we have it and it's stuck in this way that only can react E2. So even if we had, a methyl group there, a methyl group there, this isn't going to just go away. You're not going to form a carbocation. This makes the alcohol into a good leaving group, but not good enough to just leave to form the carbocation. It's going to stick around. So now what happens, we're going to form the elimination, another molecule of pyridine, which again is a really good non-nucleophilic base, comes through, and, it's going to be up here. I'm going to have to go, looks for the beta hydrogen, removes the beta hydrogen, forms the alkene, pushes the leaving group away. So the product of the reaction looks like this. So it forms our most stable alkene without the possibility of any kind of carbocation rearrangement. It converts the alcohol into a good leaving group without the possibility of carbocation formation.